Okay, now chapter 6, we're going to deal with plane stress or plane and then also plane strain stiffness equation. So this chapter is more on the plane or 2D analysis on the plane. So first we'll cover formulation on the equation. Second, we will teach you what is triangular element stiffness matrix, which this method was used in all the finite element analysis software, including ANSYS, and also if you're using SolidWorks, then this method usually is very popular in finite element analysis software. All right, and this one is using triangular form to solve. And yeah, and then some sample on how we apply the equation. All right, now what is a plane stress definition? So as you can see from the diagram here, if you look at the left-hand side and right-hand side, the differences is with the hole and without hole, but what I want you to focus on is the T, the tension reaction, the tension loading on the structure itself. As you can see, you are given Y and X direction. So in this chapter, what we're going to do is that we're going to analyze this stress in a plane dimension, meaning we're going to look at, in this case, we look at this tension in X and Y axis, and then we're going to calculate this loading in a plane dimension. Okay. All right. So when you look at the question asks you to solve plane stress, it means we are looking at there are two types of stress. One is normal stress, one is a shear stress, as you can know. So I did already explain what is normal stress, what is shear stress. And perpendicular to the plane, it is 0, meaning when you solve plane stress question, any stress that perpendicular to the plane is 0. What does it mean? It means if there's any stress, let's say this is your plane, right? This is your XY plane. Any stresses that is perpendicular 90 degree to this plane, consider 0. Okay, that means we will only consider all the stress and force that is within the plane itself, meaning parallel to the plane itself. Okay, I want you to have this concept and make this concept correct first before we move on. So we are looking at plane dimension now. Okay, plane dimension. Okay. So all these you should be familiar. Stress, we use this symbol. Shear stress, we use this symbol, and so on. Okay. So for example, normal stress, stress in Z direction. So where is Z direction? Is this way, right? This is Z. So all the stress in Z direction, we do not consider. We assume 0. So shear stress in XZ, where is XZ? Shear stress in XZ is here. This is the XZ plane. So this XZ plane also 0. Okay, this is shear XZ. Then what is YZ? YZ is this plane. This also 0. This YZ 0. Okay, so we only look at the stress that is parallel to the plane that we interested in. Okay, let's look at what does it mean. So this one I just draw to you, so you can read my slides later on. Okay, just now is stress. Just now is stress. Now is strain. What is mean by strain? Strain is a deformation. If you study your static and dynamic, strain is the L over L, means something that have changed according to the original length. Is a deformation. It's a deformation. Okay, I'll go very quick on these slides. So again, for the plane strains that is normal to the XY plane also will become 0. So as you can see from the diagram over here, you are having means deformation that is outside our reference plane will be assumed as 0. Okay. Let's look at 2D dimension state of stress and strain. In your Moodle, there is Appendix C about the derivation on the equation. Appendix C, this one. You go to Moodle and download this document and read through, because there are lots of explanation on the equation. So I will not, we will not spend time in explaining all the mathematics steps here. Okay, you go and read. All right. Our objective is how we apply the equation. All right. Now, I think you're familiar with this diagram when you study about the static and dynamic class. So you have stress and strain, stress and shear, all the dimension here. All right. This is the, we call it coupling. As you can see, if this arrow pointing here, there will be another couple that is going another direction. Same with this one. Okay. So again, the element equilibrium equation can be found in Appendix C. So the equation, how you derive it, then you go and read Appendix C. What is our main point here is that at least when you come to chapter 6, you know that when we write stress in the matrix form, we are considering x direction, y direction in, and xy direction. Again, for this chapter, we are considering x and y plane only. So the stress that we are looking at, if you write in matrix form, you write stress in x direction, stress in y direction, and shear stress in x and y plane. Okay. And then there is this is, you need to recall from your static and dynamic class, what is principal stress. So if you're given an element on the left hand side with all the stress x, shear xy, and so on, if you rotate this element at a certain degree, all these stresses on the left hand side, you will become principal stress, as you can see from the diagram on the right hand side. Okay, so meaning if you turn this element at a certain angle, in this case, theta principal or theta p, you're going to convert all these stress xy, stress x, shear xy, and so on into only 4 stresses. And in this case, you see the arrow of the principal stresses number 2 is pointing in, while principal stress 1 is pointing out. So this is a general principle that you recall from the previous module when you study stress and dynamic. Okay, so this is number 1 that you need to recall from your previous module. Okay, yeah. Any question on these slides? Anything that you want to ask me? Quite direct, huh? It's just a conversion from the left diagram into right diagram with an angle. Okay. Then another one will be this equation. I think you're familiar with this one also. When you are being asked to find uh, the principal stress using equation. All right. So you take shear stress, not shear stress at x plus y divided by 2 plus square root of x minus y divided by 2 square plus the shear xy square. You'll get this one is maximum because you need to find two. One is principal 1 and principal 2. The differences is one is positive, one is negative. One will give you maximum, one will give you minimum because one is positive, one is negative. Again, this equation is important for your coming final exam. Just take note. All right. And then how do you find the angle? This one also you need to recall from what you learned in your static and dynamic class. To find the principal angle, you take the tangent to theta equal to 2 shear xy minus divided by stress x minus xy. Right? This is also a common equation we use to find the principal angle when we have the xy and shear xy. Now, after we have cleared all the principal angle, stress and strain, now let's look at what happens when you have a deformation. Okay, so if you have a deformation of element, you can convert mathematically, as you can see from this diagram, you see the dashed line here. Dashed line here is the original element, and after a displacement and rotation happen, you can draw the final deformation as what you see on the screen here. And then there is a calculation to calculate all these parameters that you see on the screen here. All right. Now, for example, what is the original size of the element is y versus x. Okay. So what dy dx is the, if you take dx times dy, you get the area of the element. And then after that, there's a displacement or rotation happen. Then, for example, what is v? V is a displacement that from this point to this point, meaning is a y direction displacement. U also same from original to this location. Okay, this point lah, meaning point A. The displacement is U. And then if you want to find the displacement at this point also same. There is a differential equation that you can use. Del V over del Y times del Y because you are traveling from this point to this point. So there are some mathematics arrangement there, right? So you study this diagram, right? So basically it's quite direct lah. Okay. Yeah, all right. So only need to recall when we write shear in mathematics, shear strength. Mathematics form is we write du or delta u divided by delta x, meaning deformation in x direction divided by x direction. Okay, this is how we write shear strength. Y direction, same. Y direction we use v, and this is the strain. Is we type du over dy plus dv over dx. Okay, by looking at this diagram on the left hand side, you can write the fundamental equation for what is shear, what is strain. Okay. So again, there's a derivation on all this in Appendix C, right? We're not going to go back to the mathematics derivation, but I will expect you to go and read them. Okay. Actually, this one, the step is should be covered in your static and dynamic class already. Okay. So what is important for this chapter 6 is that when you write your strain in vector form, again, we are considering x direction, y direction, and xy plane dimension. Okay, yeah? So what is important for chapter 6 is you need to recall these two equations: principal stress equation, angle, and then when you write matrix, remember we only consider three entity, x, y, and xy. Happen for stress and strain also, same. This is strain. Okay, so this one is a definition when we talk about plane stress just now. So you will come to one of the famous equation, because you know that what is modulus Young? Modulus Young equal to stress divided by strain, right? You learn this one in your material science or your static or dynamic. So when you write stress equal to elasticity constant times the strain, you get your stress. So same thing happened here. It's only we change the put in the matrix form. So we write stress equal to our constant value here. We call it a matrix here, and then times your strain. Okay. So the derivation for this one is happen in the appendix C. So go and read appendix C on how to get the D. Right, I'm not going to explain about that one, but what is important again is application of equation. So you get your D equal to this matrix here. All right, so D will equal to E divided by 1 minus V. V is your Poisson ratio. V is a Poisson ratio. 1 Poisson ratio, 1 Poisson ratio, 1 minus Poisson ratio divided by 2. Okay, so this is called, important, this is called stress strain matrix, where you solve chapter 6 question. This is a very important equation, like what we learned in previous chapter, the K. When it comes to plane strain or plane stress, chapter 6, K, we no longer focus on K, but we focus on D. The D is given by this equation, or constitutive matrix. All right. Now, if you don't know what is Poisson ratio, go and read your static and dynamic or material class textbook or notes. All right. Now, just recall your stress you can write in this form, strain in this form, your D standard already. So this slide is important. This slide is important. This equation will help you to solve chapter 6 question. All right. Just now it's about stress. When you want to find stress, you refer to these slides using equation you see on the screen. But what happens if you want to find strain? Plane strain. Again, there's a derivation steps in appendix D. So if you want to find strain, the D change is formed already. Okay, the D, when you use to find plane strain, you use D equal to E divided by 1 plus Poisson ratio, 1 minus 2 Poisson ratio, and so on. This matrix, we call it also constitutive matrix, but for strain dimension. Okay, so remember there are two different D value that you need to know how to differentiate. This one is for stress. Okay, when you use stress, use this D. When you solve strain question, use this D instead. Okay. So this is the another one is that you need to recall is the partial differential equation for plane stress. You'll be looking at this equation. So what double differentiation of your u divided by the x, and this one also y equal to 1 plus Poisson ratio divided by 2, and so on. This is another form, right? It's another form. The differences is this one is focused on u. I can see the u. This one is focused on v. What does it mean? Mean the first equation here is referring to x direction. This one referring to y direction. Okay. So just look at the structure of the mathematic form itself. You manage to decide which equation to use. If the question asks you to find plane stress in x direction, then you use the above equation. Then if the question asks you to find y direction, then you use the below equation. Okay, the next one is important because this is the fundamental concept when you are using FEA or finite element analysis software. This is a fundamental theory or understanding you need to have. If not, then you're just merely a user on the software. So we train you to become an engineer, so you need to know what is the background of the theory used by the software. Okay, let's look at this diagram. So this diagram is directly give you y and x, and then you have the v, which is a displacement in y direction, u in x direction, displacement in x direction we denote as u, and we have one plane here, and this plane is very thin, very thin. This plane is given you by this blank here, and you're having a tensile loading TS on the left and on the right. Means this was pulling to the left and pulling to the right. Okay, so when you look at the word T, you mean you already have to understand this is a tensile loading. And if the force is pointing in, it becomes compressive. It becomes compressive. All right. All right. As you can see here, I add in one more diagram, which is when you use ANSYS software, for example, or you use SolidWorks to do simulation software, to do simulation procedure, you will go through a procedure called discretization, or there's a procedure called meshing. Okay, so in the textbook, we use this word discretize or discretization. In the software, you will come across there's a function or there's a step called meshing. So this basically is about how meshing is happening in the software. All right. So if you compare the above diagram and the below diagram, what is happening is that we are converting this rectangular into multiple triangular that you see on this diagram. Okay. Now take note now. We are converting big surfaces. We chop them into a small pieces so that we can run simulation or can do analysis pieces by pieces. Then we combine them together. Okay. So as you can look at the diagram, focus on the diagram at the lower corner of your screen. There is a notation come up. So you have N, you have I, you have J and M. What does it mean? Later in the equation that you see, it follow this sequence I, J, M. I, J, M. Okay. So what do you think? This numbering is clockwise or anti-clockwise? What do you think? Ashma, what do you think? This numbering is following clockwise direction or anti-clockwise direction?
Anti-clockwise.
It's an anti-clockwise direction because I, J followed by K, but we use M instead. Why? Because K is famous in this module. K was used for stiffness matrix already, so we do not use K, we use M instead, not to confuse the symbol. Right? So again, this is important concept. Our I is one of the corner followed by anti-clockwise numbering. I, J, M. So no matter later in the test later on, no matter how you do it, for example, I give you 0.1, 0.2, 0.3, you have to know that if you do numbering, you can number this one as I, followed by 0.3, not by 0.2. It must be anti-clockwise numbering. So 0.1 will become I, 0.3 will become J, 0.2 will become M. Remember the numbering sequence is important before we move to a more complex equation. Yeah. Once you understand this one, you're able to do. Okay, IJM we covered already. So let's look at the steps. Let's look at the steps. So first, same when we do finite element analysis. First one, we look for element type. Second, we look for function, displacement function. Third, we look for strain displacement, stress strain relationship. This one we already covered in the since chapter 2, chapter 3, chapter 4. We're using the same 7 steps. 4, derive the matrix and equation. Then we assembly become global, do the superimpose, and then we use the boundary condition to cover our matrix. Then we solve for the unknown, the rest, the remaining one. So this 7 step is very important for this module. Actually, we will start using these 7 steps since chapter 2. Okay. So for chapter 6, we also use these 7 steps. So first one, when you come to chapter 6, it means we break the above diagram into small pieces of rectangular. The process called discretization. In the software, the process is called meshing. Okay, it's called meshing. So this I expand the small diagram here. I expand into a red box that I highlight with the red line, means it's very important. So these are the coordinate and numbering that we'll be using in our equation later on. So the first one, we always start with the left-hand side node. We label as I, followed by anti-clockwise direction J, the third point is M. Okay, next you will look at the displacement in Y direction and X direction, meaning one point will give you UI, VI. Okay, UI, VI. So one point will have two displacement, and the coordinate of that point, I, will give you XI, comma, YI. This is the Cartesian coordinate. Because later, we will substitute this value into our calculation later on. This is a very important diagram. It's like a roadmap. So once you understand this diagram, you can solve almost any question from chapter 6. All right. So later on, you will see a very bombastic, very complex mathematics structure kind of equation. But don't be scared by all these mathematics later on. As long as you understand this red color box diagram, you just plug in what you see from this diagram, compare to the question, then you manage to solve the question by using the equation you see later on. All right. Give you another 10 seconds to look at this diagram. Again, I, J, M. Each one will give you two displacement, V, U, but labeled as I according to their location. The second one become V, J, U, J. The third one become V, M, U, M. And the coordinate also labeled as XM, YM if you're referring to point M. If you're referring to point J, you label as XJ, YJ. Clear? Any question on this red box diagram? Okay, no question, I'm going to move on. All right. Now, recall back what is displacement. Again, we like to write displacement in matrix form. So matrix form, we will consider displacement in I point, J point, and M point. So we have 3 points. So each point will give you displacement. And each point have two displacements. So later you're going to expand this displacement into UI, VI, UJ, VJ, UM, VM. Okay, by sequence, I, J, M. Now, students normally make mistakes. What students like to do? They will like to do their own Lego together. They like to write like this. They like to combine all the U together, which is wrong. We have to go point by point, meaning point I have two displacement. Point J have two displacement. Point M have two displacement. Don't make the mistakes on the right hand side that are right here. Okay, and we are quite consistent with our previous chapter also. We go point by point. Okay, clear with the displacement? Sue, you clear with the displacement?
Okay.
Okay, huh? All right. Brian, you okay with the displacement? Brian, are you there?
Yes, sir.
Are you clear of these slides? Do you understand
Yes.
the meaning? Okay, important. You get the concept correct, you can solve a lot of questions. The next one is the displacement function. So we always start with a very simple equation. We start with the linear displacement function. And this is the polynomial polynomial equation in the linear form, meaning you write u, this is the function, u in the xy direction. So you can write u equal to a1 plus a2x plus a3y for u. V the same. V in xy direction, you use a4 plus a5x plus a6y. So you are using a linear displacement function to derive the equation later on, or to derive the matrix later on. So this is the starting point of our matrix later on. So u equal to this equation, v equal to this equation. Okay, then we put in the matrix form. We put into matrix form. The blue color two equation we put in the matrix form. We use a new symbol for today. This symbol. Okay, is a displacement function. We use this symbol. Right. I forget what is the name of this symbol already, but this is a symbol we use to represent the displacement in u and v direction. Okay, so we combine these two into a matrix form like this. Then after that, I put in one side of the screen here. This is your u equation, v equation, and then we just introduce you one new matrix form in the new symbol that you see today. For a general displacement function, we write in this form. Again, you're seeing curly form. You can rewrite into a proper matrix form, which means you see the bracket. Bracket means a constant value. I try to avoid use k, but it will be similar to a constant value matrix, where every time you see a square bracket means there's a constant value inside this matrix. All right, and then the left hand side is all the unknown. Okay, yeah. So far we're still scratching the matrix method in converting the equation into matrix form. Try to observe, especially it is quite easy. So on the left hand side, this matrix is all the unknown that we have in the equation. So if you count these two equations, you have 6 unknown there, a1 until a6. So you write a1 until a6 in the vertical matrix form, and then you derive the equation. So for example, how you get the first matrix on top, how you get a1. Okay, so actually this one, okay, so this one, 1 plus a1 plus x times a2 plus y times a3, you're going to get the first equation. Okay, you get the first equation for the first row. Then the rest is not relevant because first equation you don't have a4, a5, a6, so you put 0, 0, 0. You do the same for second row of matrix. You don't have second equation, you don't have a1, a2, a3, so you put 0, 0, 0, and then you put 1 times a4, x times a5, y times a6. You get the matrix form like this. Okay, makes sense to you? Any of you don't understand what is happening on the screen here? Makes sense to you, right? Okay, next. Now, the objective of next slide is want to find what is A. What is A, right? So we start using the coordinate that we have in the red box just now. For example, we use I location. U location, we have U in X and Y direction, right? For U, we have X and Y direction. So for the I point, I mean this one. You see this one? Ui. You can write in this equation, meaning ui or I point x direction displacement, it can move in x and y direction. So you can write for displacement, okay, let's say this is your u point. You know that your u point, u point, I point, you have two directions. You have ui and vi. And the location of I is xi and yi. So we are looking at ui first. Ui means that displacement in the x direction, or in the x direction, but focusing on I point. You can write in the linear equation a1 equal to a2 xi plus a3 yi. Okay, you just modify the equation from the top. You modify, you substitute the x and y value. For I, you will get this orange color equation. A1, A2, X become Xi. A3 copy, Y you modify to Yi. Okay, try to understand this equation first. Yeah, is actually a substitution of coordinate into the blue color equation. Next, you do it for J point, but in U direction. You get the second equation. Again, substitution of coordinate of J. J, you have xj and yj. What does it mean? If you recall back this red color box here, I will show you the red color box, big one. You see each coordinate, each point have coordinate. This is I point. I you have xi, yi. J you have xj, yj. M you have xm, ym. So you just substitute this coordinate into the function here. So the first one we look at I, second one you look at J, you substitute, the equation become A1 plus A2 xj A3 yj. Just substitute the J location. You do the same for M, you get the third set of equation, A1 plus A2 xm plus A3 ym. You do already completed for U. Now you do another step for V. So VI means in Y direction. Again, V, what is the equation? Is this one. So you just substitute the location of X and Y into this equation. So you'll be seeing equal to A4 plus A5XI plus A6YI. You repeat the same for J and M coordinate. You get another 3 set of equation. So total you have 6 equation here. Before you move forward, any one of you are not sure how to get this 6 equation? Quite clear. Basically, we are applying these two blue color equation by substituting all the coordinate of the point. All these coordinate of the point, we just substitute inside these two, we get 6 equation. All right, again, we are still looking at I point, J point, M point. We are looking at triangular shape of element here. Okay. Next, we're going to put them into matrix form, where you already learned just now. I did show you how to do it in 2 equation here. Now you have 6. You change this 6 into matrix form. Okay, it should make sense to you. So the U, how you write in matrix form? So because these three only have three unknown, A1, A2, A3, A1, A2, A3, A1, A2, A3. So the curly bracket here consists of the unknown, A1, A2, A3 only for U direction. While on the left hand side is what you see, these three, you just put on here. The K matrix is what we derived just now. Follow the steps. For example, how to get this equation? You take 1 times A1, you get this one. How to get A2 x1? You A2 must time x1, right? So you write x1 for this position. How to get A3 y1? You already have A3, so your yi is missing. So you write yi in this location. Yi plus this one. You repeat the same for second one. Repeat the same for third one. You get this matrix. Any question on how to get this matrix? Stop me if you are not sure. Stop me. But if the explanation is logic to you, makes sense to you, then you are okay. Stop me if you are not able to absorb or you're not able to see the logic, how you get the form of this equation on the left hand side. Stop me. All right, then you do the same for the V. You do the same for the V. Just test your understanding. Ashmal, what should you write on this column? You get the same format. What do you think if you derive this 6 into matrix form? What should you write on the left hand side here?
VI, VJ, VM.
Correct. Excellent. Sue, what should you write over here for these three set of equation?
A4, A5, and A6.
Correct. Oh, seems you understand already. Very good. Chia, do you want to try the first row?
1
1
xi yi.
xi yi. Brian, you want to try the second one? This one.
Second one is 1
x5
xj
xj
yj.
yj. So I think this one you also know lah. I don't need to ask already. Okay. All right. Seems the class able to absorb. Very good. Okay, so I will. Okay, this one is another fast forward lah. So this slide is just that how you solve for A1, A2, and A3. Basically, you just pull this matrix to the left. It means you do an inverse matrix of this X. All right, you just inverse this. You pull to the left, you get an inverse matrix times the U here. Okay, you get your A. All right. Okay. So how to do the inverse matrix again is inside the appendix A. I just show you the results lah. Okay. First, you need to find the cofactor and so on lah. So yeah, you will get all this value, but I will just give you the final answer. For example, what is this form when you do the inverse matrix? Meaning this whole thing when you do the inverse matrix, what will you see? You will see in this form. Right? When you do inverse matrix of this whole thing, x inverse will equal to 1 over 2a, and then you will see all the value after you do in inverse. I will label, simplify the new number as alpha 1, alpha j, alpha m, beta I, beta j, beta m, gamma I, gamma j, gamma m. This is a new number after you do the inverse matrix. So just give you some convenience. What is 2a? 2a is this matrix. 2a, how you find determinant of a is using this one. Mean 1 xi, yi, 1 xj, yj, 1 xm, ym. What is xi? Is a location of your x here. If you look at this red box, it's a location of your I x location. It's just a substitution of all the coordinate number inside the matrix. Okay, so we just plug and play kind of game. So, and again, I already introduced you the online matrix calculator. You managed to find the determinants of 2a very fast. You just need to key in these these 9 numbers inside the online calculator. Press, then after that you press to find the determinant of all this number. Okay, so in meaning, if you calculate the value manually, how you get 2a, you take, okay, this is the mathematic ways lah. So how to get 2a, you choose this one, mean you close this one, close this one. I think you can recall from your advanced mathematics or calculus class how to find determinant. I think this one Engineer Ma will teach you lah. Okay, so when you select this one, you only left out these 2, right? So you take this one minus this one. Okay, 1 plus ym minus yj and so on. Right? So there's steps there. So you get this one and so on. So basically, A, what is A? A is the area of the triangular. A is the area of triangular. So by using this matrix determinant, you manage to find the area of the triangular by using this equation. Okay, now for example, 2a, after you substitute the location of xi, you substitute yj. Yj means, yj, where is yj? Yj is j point, y location, this one. You substitute here. What is ym? Is m node or m point, but y coordinate, this one. After you substitute, you get, let's say you get 100. Your area is not 100, but you have to area, because 2a equal to 100, your area equal to 50 unit square. Okay, 50 unit square. So this is how your ANSYS software or SolidWorks find the area of that particular element. It uses this formula. Make sense to you? All right. That's why sometimes in the calculation in your software, for example, ANSYS, it will come up error. It will tell you the area of your element is too small, or area of your something of your element is insufficient for solution or something. So this is the fundamental equation used by the software. Okay, so again, this is important software, important equation to solve for area. Okay, and all these are standard. What is alpha I? Alpha I equal to xj ym minus yi xm. So what is xj? You refer to this diagram. Xj means point j, x coordinate is one. Ym, what is ym is m point, y coordinate. This one. You take x times this this coordinate times, and then minus yj xm, and so on. Any question on this simple equation? Because you have 9 equations you need to solve. I'm only show you 1. But the step is very direct. First step, from the question you copy, and then you label what is your I coordinate, Y coordinate, I coordinate, J coordinate, and M coordinate. Write out all the numbers as you see in the red box here. And then you open up these PowerPoint slides. You substitute the numbers and find what is alpha. What is alpha I, for example. Clear? All of you clear? So I don't expect you to memorize, but at least you know where to find all these equations. I show you the first one. I'm going to show you all the equation for 9. These are all the equation for 9 point here. This is an important slide. Anyone of you have question? Anyone of you're not sure, what is this? What is xi? What is xm? You don't understand. Ask me now.
No, sir.
Clear? Okay. Quite direct, So remember, this is a very important slide. Because later, we will not go back to explain what is alpha I anymore. Later slides or further slide after this, you will see symbol alpha I, beta J, gamma M, and so on. So this is important slides. So memorize or remember there's a slides that teach you how to calculate the value of all these 9 numbers. Okay, then the next, it just means that if you want to calculate what is the A1, A2, A3, you just substitute the definition that we derived just now, because the inverse of x was given by 1 over 2a and 9 alpha, beta, gamma number here, times the uj, ui, uj, and um. Okay. And then use a similar way. You're going to find what is your A4, A5, A6. Same. Okay, yeah? It will be the same for A4, A5, A6. You see the matrix is same. All right? Okay. So we move on to the next slides. So this is how we derive the equation put in the matrix form. For example, the u equal to a1 plus a2x plus y, we write in the matrix form like this. U equal to 1xy bracket, square bracket plus the curly bracket, a1, a2, a3. And then the recall just now, we just learned what is a1, a2, a3. All right, by this equation. So you just substitute inside there. You're going to get a very long matrix. So your U matrix now become a longer matrix. 1xy, 1 over 2a, and all the gamma, alpha, beta, gamma form times the uj, uijm. Right? So far, anything look very weird to you? No, right? Everything makes sense to you, right? You expand the equation. Okay, you expand the equation. So this one is just a substitution of equation. You pull the 2a to the left. Then you expand. For example, how to get this one? This one times this one, you get this one, plus this one, plus this one, you get the first number. and so on. You continue doing the mathematical equation, you'll get a very lengthy equation in a blue color. I just do it one sample for you. So meaning, how you get this one? Meaning 1 plus this one, plus this one, plus this one, plus this one, plus this one. It's going to be a very lengthy equation. But the concept is there. Okay, the concept is there. All right. Move forward. So just now, we did show you how to get this very long equation. You do the same for V. You get this lengthy equation again. But what is changes is the rest is still the same. The constant still the same. Only the displacement change from U to V. U to V. U to V. Okay, now we have two very lengthy equations. As you can see, what's happening for the past 15 minutes, we change a simple equation of A1 plus A2 x plus A3 equation into alpha, beta, gamma, and that particular UI location, UJ location, and UM location. Okay, we already changed the simple equation into alpha gamma term and also displacement in I point, displacement in J point, displacement in M point. Now, we try to reduce this complex form into a more simpler form. So we write Ni, capital Ni equal to 1 over 2a alpha I plus beta Ix plus gamma Iy, which is this whole thing. We simplify into capital Ni. So it will look simpler later on. Which means you do the same for the second one, third one. So second one is you use Nj because it's in the J dimension. So that's why you use capital Nj to represent the second constant value here. Okay, you do the same because the third one is representing or pointing to the M location. So we are using Nm to represent the third constant here. Then it will give you the equation is more simpler form in the N, capital N form. So you are writing U equal to NIUI plus NJYJ, NJUJ plus NMUM. You do the same for V. Same. What does this N form? N, there's a name for it. N is before this we see this capital N before. Is a form factor. Okay, it's a form factor. If you study vibration, then you will hear this term before. Any question for these two equations? Why suddenly we can come up with this? Any one of you don't understand? Why suddenly there's a yellow color capital N there? No, right? Because we simplified the equation with this one. So again, later we will no longer rewrite this 1 over 2a alpha I plus beta x plus gamma I y anymore. Later you'll see Ni, Nj, Nm. So at least you know where to find what is Ni. Ni is equal to this one. Nj equal to this one. Nm equal to this one. Okay. So we have these two equations. And every equation we can know that we can put in the matrix form again. So matrix form is this one. So how do we write? We can write this equation in this form. We change these two equations in this form. In the general displacement function, so you have your constant matrix, which consists of n form and the displacement of ui, ui, vi, um, vj, I think this one is, sorry, I think this one is wrong. This one is uj. Yeah? So take note, this is a typo error in my slides. This should be uj, not um. Okay? Because when I copy and paste, when I type the formula, it should be j. Yeah? So just take note, there's a typo error here. So I think you can see the flow of derivation over here. All right. So how to get this K matrix? So n1 times v1, you get this one. There's no v1 in the first equation, so 0. Then how to get this one? You add in nj times uj, 0. There's no vj in the first equation. Same with the rest. Okay. Again, typo error in my slides. This is not but it's uj. And the objective of all this explanation is that we just show you that you can put your general displacement function in the form of n time displacement. Okay, n time displacement. So this is when you plot in graph, or when the software that you use to do the user interface presentation, meaning you see the graph, the vector form in the ANSYS software, or even in the SolidWorks or other FEA software, you will plot, you see y versus x, and then there is a form factor ni. There you see there's an arrow pointing up and down and so on. Okay. Okay, any questions so far? All right. Okay, let me check if I can go further a little bit. Okay, I will go a few more slides, then we stop. Give me another 2 more minutes, then we stop. Okay, this is what mean by if you study FEA or finite element analysis. There's one term called unstressed element. Unstressed element means if you see all these elements, the solid color and the dash color, it means that you have a rigid body that only do transition. Means it move from one point to another point, there's no deformation. Okay, this one move up or move down, this one rotation and so on. Okay, this is an unstressed element in the cantilever beam. So this is a constant strength triangular, meaning if you have an unstressed element like this, so you see a deformation from the top to bottom. So if you're pressing the stress by distributed load like this, so the software will, after you do the calculation, the software will show you the behavior, the displacement after a certain time. So it will show you the displacement of this one. Now after that, before this, I show you what is for stress. Now you do the same process for the strain. I'm not going to repeat all the steps, but you will repeat the same similar calculation steps, but now you look at the strain by using the strain definition. Again, you write in matrix form for strain, and so on. And then you get two equations. You repeat the same. You're seeing the A1, A2, A3 equation, A4, A5 equation. But now you are at the strain dimension. You repeat the same. All right, you repeat the same. So A1 is what? A1 is stress S. EY is A6 and so on, right? So I'm just showing you the slides very fast. You derive the same equation. You have the U and V with the strain equation over here. You derive them and then you arrive at the same N and U form. Okay, N and U form. So again, you are referring to the same N value for the stress, for the strain also. Okay, so these are the formula that you use to calculate the N value. Okay, for the N value. Read through the slides. All these are the derivation steps. Okay, then you write in the matrix form again. You put them back. So you are seeing the B. In this case, if you are dealing with strain, you're dealing with strain, you are seeing B. Okay, B equal to something that you can see on the screen here after you derive the equation. Just now, for stress, we are using, let me see here. Okay. Maybe special for strain, we are using B to differentiate the alpha, gamma, and beta. So as you can see, for strain, we are using beta, using a capital B to represent what they are. Okay. So for strain, you have the strain equal to BD. Just now for stress, we are using capital D. Okay, times the strain just now. So we are deriving what is strain. So later we are going to substitute this one inside here. It's going to be a very long matrix. Okay. So at this point, is that important you understand what is B matrix. B matrix consists of BI, BJ, BM. What is BI? You refer to these slides. BI equal to this matrix form. BJ equal to this matrix form. BM equal to this matrix form. Okay, the detailed derivation you can refer to my slides. Then you put the stress and strain together. Stress equal to D strain. D equal to this one we defined before. And then recall the definition I showed you just now. You put everything together. You manage to find your stress by using D matrix times B matrix times the displacement of the system. Okay, B matrix is this one. B matrix is this one. Calculate BI, BJ, BM. How to find BI? You use this matrix. How to calculate BJ? Use this matrix. How to calculate BM? Use this matrix. Okay. Now, what is D? D, you use this matrix. So basically, this is a conclusion for today's lecture. How to find stress? You use stress equal to D matrix times B matrix times the displacement. Okay, we stop here.